In the main demonstration, we've seen how SolidWorks simulation helps in quickly sizing parts, but it has far more capabilities to help in meeting many design challenges. In determining performance of the overall boom design, we can use SolidWorks simulation to quickly locate high stress areas in need of more detailed analysis. The boom contains two main actuators that combine to raise or swivel the arm, and an internal actuator for extending the boom out. We can represent bolt and pin connections to simplify part connectivity and easily get joint loads for sizing. Bushings can also be incorporated to account for compliance in joints if desired, or used as rigid connections as well. Fixed connectors are used to represent the hydraulic pressure holding the cylinders in place so as to determine the resulting loads and stresses in specific configurations. The automatic bonded contact detection simplifies model setup when dealing with lots of parts and complex geometry. This model only takes a few minutes to solve, and the great post-processing options in SolidWorks simulation make it straightforward to gain insight into the performance of the boom. The section cut plot allows you to look inside the model at any location and visualize a stress or deflection or any results such as for the internal actuator area. You're also able to create plots on specific faces or bodies to look just at areas of concern such as the mounting location for the main actuators. Just select the faces or parts on the screen and only results for those entities will be displayed. When it is time to gain a better understanding of load paths and local stresses, SolidWorks simulation provides detailed results and can simulate complex interactions. For the case of the knuckle joints supporting the main actuators, there is complex pin bending loads that need to be accounted for to accurately represent the part connections. Taking the case for a symmetric load condition, we can modify just half of the mounting plate and then focus on parts of the geometry we wish to study. This includes bolts to hold the pins in place with a preload and defining no penetration contacts for the surfaces in the joints such as the pin to bushing contact. We then apply restraints at the mounting holes and back face and then the actuator force using a bearing load to correctly distribute the load over the faces of the knuckle. After running the analysis, we have the ability to review and store results for the whole model or just components of interest to easily understand where the most highly loaded areas are. The contact pressure plot shows clearly where the faces are pushing on each other under the loads. For more detailed analysis, we can focus on a further subset of the model and gain clearer understanding of the local stresses in the knuckle. We've assumed that we can hold the main pivot pin and support the normal direction on the wear plates. There are still no penetration contacts defined between the knuckle and the bushing sleeves. By reducing the model to only a few parts, we can obtain far more detailed results in a faster time frame. Local mesh refinement was added in areas of interest and high stress areas to ensure accurate results. Isosurfaces aid in visualizing the highly stressed portions of the geometry. In this instance, stresses above 50 megapascals. For the knuckle, we can investigate the option of reducing material without sacrificing performance. If we simplify the model to a completely bonded series of parts, which is similar to what we had in the main demonstration, then we can compare results to the more accurate representation and observe how closely it correlates. The Compare tool makes this very easy. You simply select the studies and result plots you wish to compare, and these are then displayed side by side on the screen. The stresses in the simplified model appear slightly conservative, but match very closely to the more accurate model, so it should be suitable for use in sizing the main knuckle geometry. Using a design study, we can optimize the fillet size in the knuckles as well as the flange thickness. We specify the model dimensions to vary, our constraint, in this case a maximum stress of 250 megapascals, which is a yield, and our goal, which is to minimize weight. The result interface highlights the best design in green and any that didn't meet our criterion in red. We are even able to view simulation results for any of the iterations run to aid in visualizing the results. SolidWorks Simulation also supports nonlinear analysis for modelling material yielding, as well as large deformation and high-speed collision. For the mining industry, preventing the roof from crushing under falling debris is a critical requirement. A standard test is used dropping a finite weight with a specific amount of energy to ensure the occupant is not harmed. The setup for this is very straightforward. We use a plastic material model for the A36 steel, and then define a no penetration contact for the weight impacting on the roof. An initial velocity of 10.11 meters per second provides the required impact energy for the test standard, and then we add a few restraints to guide the mass and hold the roof structure at its mounting base. The impact occurs very quickly, so an analysis is only run for 15 milliseconds. The stress results show some regions yielded when the impact occurred and did not return back to the original stress state. The displacement plot shows that there is relatively large deformation. Using the selective part display, we can focus just on the roof and see that it deforms a maximum of 26 millimeters at the time of impact. Being able to display just a section plot makes it very clear what is taking place in the structure at the time of impact. But numerical results over time tell the whole story. Using sensors, we can monitor the different stresses on all or part of the model and then plot these over time. Looking at the average stress over the contact face against time, it's clear the stresses spiked above yield during impact and that there was plastic deformation as the stress did not return back to zero. Looking at the maximum displacement shows a similar result with a permanent deformation in the roof of around 20 millimeters. Animations of the results reinforce this, showing the load transmission through the structure over time and the yielding and deformation that occurs. It is far less expensive to test this on a computer than to do it for a real test in production. These are just a subset of the powerful capabilities available in SolidWorks Simulation to help meet your design challenges.